In this work, we present a model-free adaptive dynamic programming controller that learns to track desired trajectories optimally with respect to a given objective function. We therefore present a Q function which explicitly incorporates a local approximation of the reference trajectory. We apply the model-free ADP algorithm to the real-world large-scale ball-and-plate system, which can be seen on the right. Finally, we compare a model-based controller, a model-free ADP setpoint controller, and our proposed model-free ADP tracking controller. At each time step k, we approximate the reference trajectory by r. Here, ρ is a basis function and pk is a weight that describes the local reference trajectory. The shifted reference trajectory pki is defined as shown. This shifted version of pk is needed in order to fulfill the Markov property in the ADP training data. Then, the Q function, which explicitly incorporates the local trajectory approximation, is defined. The optimal control law finally results from the minimizing control input of the optimal Q function. We approximate the Q function by a quadratic function of u, x, p, and a constant. The constant term allows the ADP controller to learn an additional offset correction term. The estimated optimal policy directly results from the approximated Q function. The Q function and the policy are updated in an iterative procedure using measured data from the real ball-and-plate system. In the first step, the ball-and-plate system is excited and data tuples are stored. Then, we use least squares policy iteration in order to train our controller iteratively. On the left, the resulting tracking performance of two setpoint controllers can be seen. In yellow, the model-based controller is shown, whereas the learned ADP-based controller is given in blue. In the top row, the trajectories are given. The bottom row shows the resulting cost. In the middle, the results using quadratic polynomials to locally approximate the reference trajectory are given. The model-based controller is shown in green, our ADP controller is given in red. It can be seen that the setpoint controllers lag behind and the local reference approximation allows foresighted control. Further, our ADP-based controller outperforms the model-based controller. On the right, a tracking example is shown for the ADP controller where the reference is approximated by means of a quadratic polynomial. Thank you very much for your attention.
Good morning to everyone. I'm Ninad Gaikwad, a PhD candidate at University of Florida. I'll be presenting the paper titled Reinforcement Learning-Based Home Energy Management System for Resiliency, co-authored with my colleague Naren, Professor Barua, and Professor Mine. The powerful winds associated with extreme weather events like hurricanes cause damage to the transmission and distribution system of the power grid, leading to extended power outages. For residential consumers, extended power outages result in rotting food in the refrigerator, thermal discomfort, and no lights at night, effectively reducing their standard of living to the level of 19th century. Our goal is to provide reliable energy supply to a house for maintaining habitable conditions during extended power outages at reduced cost and reduced real-time computational effort. Distributed solar generation can provide a resilient energy supply during extended outages. However, as the average household load in the US is quite high, serving the entire household load from an on-site PV battery system will require a large system, driving up costs substantially. In our prior work, we showed that an intelligent controller based in MPC provides the same level of resiliency performance as that of the baseline controller with half the system size, effectively reducing cost by half. It does this by exploiting flexibility in generation, where it decides optimal scheduling of the PV battery system, and flexibility in demand, where the refrigerator has higher priority over lights and fans. However, there are some challenges to the MPC controller. The first challenge with our prior MPC controller is that it requires simple yet accurate models as it involves real-time optimization. And the second is that the discrete actuation for residential loads makes the underlying optimization problem a mixed integer program, which is challenging to solve. In this work, we propose an RL-based controller, which is an attractive alternative to the MPC controller in our application as it is model-free and its real-time control computation is simple. We utilize SAPQ learning algorithm for training our RL controller, where we use linear parameterization for approximating the Q function. The real-time implementation of the RL controller ends up being finding minimum over 15 values, which makes it computationally trivial to solve. We observe that the proposed controller provides the same level of resiliency performance as compared with MPC controller, with a reduction in computation time by 5 orders of magnitude without the need for any proprietary solver. The proposed controller maintains the refrigerator temperature within bounds for the entire simulation period, keeping the food safe, while there were large temperature violations in case of the baseline controller, leading to rotting of food. We will be eagerly waiting for any questions and to have detailed discussions during the digital poster session. Thank you.
My name is Koen Klassens, and welcome to this pitch on the real-time tracking control of photopolymerization for additive manufacturing. Evidently, we need control algorithms in order to effectively print 3D products. So for instance, accurate motion control of the actuators allows to print complex shaped parts such as the one shown. However, at the microscale, defects such as delamination are often still present, and problems at this scale deteriorate the material properties of the end product and therefore prevent the widespread adoption of hot photopolymerization in the high-tech industry. In essence, the main unresolved issue that we have is the insufficient consistency and repeatability due to, for instance, variability in the printing process, variability in the feedstock materials, and variability in the equipment. It is commonly recognized that an in-depth understanding, in situ process monitoring, and control of the UV curing process are crucial in order to improve defect-free end products of high quality. The current state of the art is simply turning on the actuator, in this case the light source, at full intensity until the material has solidified. In our proposed approach, the actuator intensity is modulated and the curing degree is measured by means of spectrometry. This provides the means to control the temporal evolution of the curing process throughout the layer, which in turn will yield better and more consistent end products. An extension to the quadratic tracking framework is introduced, which we will use to anticipatively control this nonlinear system. For this purpose, an updating strategy is proposed based on the sequential linearization of this inherently nonlinear model. By means of this anticipative tracking control strategy, we illustrate the potential of our approach at this intermediate one-dimensional scale. So here, for instance, the average curing degree throughout the layer successfully tracks an arbitrary reference signal. In addition, we experimentally have proven the principle at the zero-dimensional voxel scale. So at this zero-dimensional point, which is mimicked through this experimental setup, we illustrate that arbitrary reference signals can be tracked. And these results are promising and they resemble the first steps towards machine scale application. So to conclude, in this paper, the potential of model-based curing control is successfully proven through simulations and an experimental validation, and this result can be considered as a fundamental step in additive manufacturing towards improved, consistent, and reproducible product quality.
Good afternoon. My name is Maxim Faronov. I'm a PhD candidate in Western University, Canada, and my supervisor is Dr. Ilya Poloshin. My topic for today's presentation is observer-based control of drilling mode in rotary drilling systems. The purpose of this research work is increasing the efficiency of drilling by development of new methods and algorithms for automatic control of drilling processes. We address two problems, regulation of the vertical penetration rate and the regulation of the drilling power under some limited conditions. It is assumed that parameters of the environment are known beforehand. Most of the drilling systems parameters are known, and only measurements on the ground level are available for the controller. We use a rather simple finite dimensional model of the drilling system, where rotational dynamics are represented by a system of linear differential equations with the motor voltage as a control signal and reaction torque or torque on beat as a disturbance. It is interconnected with the translational dynamics and the beat torque interaction through nonlinear component, which is called depth of cut. In order to design a proper control signal, first we generate the reference angular velocity that solves the control problems using a speed gradient algorithm. After that, we built a rotational dynamics controller, which ensures tracking of the reference angular velocity and rejection of the disturbance. This controller is based on two high-order sliding mode observers that allow to estimate downhole variables as well as some higher derivatives. Eventually, it is a sum of three components: proportional control, tracking part, and disturbance rejection part. For validation, we simulate several rock layers with different hardness and define the desired level of vertical velocity or Jillian power. Simulations confirm that the estimates converge to the actual signals, and the reference signals are tracked almost perfectly in every rock layer. In conclusion, we successfully addressed the problems of vertical velocity and Jillian power regulation in rotary drilling systems. And our approach doesn't require underground measurements or knowledge of the rock properties, while using a relatively simple model for a controller. Thank you for your attention.
Hi, my name is Burak Ergöçmen. This presentation is about reconfigurable dynamic control allocation with state-dependent Riccati equation as a fault-tolerant flight controller for NASA GTM design. Problem: survival of the aircraft is critical during an emergency, especially for the loss of control in flight, and it leads to fatal consequences. The solution is reconfiguring the flight control computer. Control allocation is reconfigured in real time. However, STRE is tuned already for recovering smoothly during minor emergencies. NASA GTM design is used as a nonlinear model. These are contributions of my paper. First, STRE is used effectively with the CEA. There are two limited studies in the literature about that. Second, STRE is tuned as a passive FTFC before an emergency. Some trials show that tuning of the STRE only for the routine flight can be detrimental during an emergency. Third, after reconfiguration of the control allocation, some parts of the elevators become elevons. It's a straightforward but novel approach. Fourth, there are very limited control application papers for NASA GTM design. Why do we choose STRE and dynamic control allocation? Because STRE is a nonlinear controller and easy to implement. Dynamic control allocation can take into account actuator constraints, be configured easily, useful for overactuated aircraft. What is control allocation? The inverse of the BCA matrix cannot be calculated because it's a 3/8 matrix. So one of the CA methods, dynamic control allocation, is used, and weighted least square equation is given here. Dynamic CA and reconfiguring it, it's not a new thing. However, first, elevators become elevons with control effective metrics and steady state distribution metrics. Second, emphasizing the importance of the weight metrics and reconfiguring it during worst cases are new things. How do we reconfigure the controller, for example, during both ailerons stack? Too easy, with numbers. These are for activating elevons. These are for excluding ailerons. It is for decreasing the roll moment undesirable effects, and without it, the result is loss of control. All these matrices are in the reconfiguration block regarding different type of emergencies. Problem in here is lock in place for the right aileron at 15 degrees and for the left aileron minus 15 degrees. If the reconfiguration for the control allocation is not executed, the result is loss of control in flight. However, if reconfiguration is done and elevons are activated, loss of control is prevented. You can read my paper for details. Thank you for your attention.
In this 3 minutes video, I'm going to introduce a comparative study on multidisciplinary and multi-objective optimal design of an aircraft wing with under three different configuration. So we have two objectives in this study. The first one is to study the multidisciplinary and the multi-objective optimal design of an aircraft wing under three different configuration. We have aircraft with 2, with the 3, and with 4 control surfaces, and then we are going to compare the performance of the wing by considering 3 objectives. The first one is the ability of the closed lobe to reject external disturbances, and the other one is the stability robustness, and the third objective is the energy consumption or utilization. So we need a model. This model can be configured for 3 different, for 2, 3, and 4 control surfaces. So this is the mathematical equation that we are going to use as a model for the system, and then we convert the matrix differential equation into a state space equation that we use in the control system design. This is how the system matrices are related to the matrix differential equation matrices. Then we design a full state feedback gain matrix by using LQR and KC, which is the feedback gain matrix, is given by this by equation number 5 by minimizing this performance index. Q here is the state weighting matrix, R is the control weighting matrix, and as you can tell that Q and R will affect the value of KC because P is a function of R and Q, as you can tell from equation 7, and it's also a function of R. We are going to talk more about the design objective during the poster session. These are the 3 objectives that were selected: improving the stability robustness of the system, the ability to reject external disturbance, and also the energy utilization. 3 objectives, and we have the design parameters, which includes the design details of the LQR algorithm, linear quadratic regulator algorithm, in addition to the sizing of the control surfaces. Okay, so more about this will be discussed during the poster session. We have some of the constraint. We get the Pareto France, and then we start the comparison between the performance of the wings with different configuration. I would like to thank the Air Force for the support and for the grant during the summer fellowship that helped me to study and to accomplish and to finish this work. Thank you very much.
Hi everyone, my name is Sun. It's my great honor and pleasure to introduce my recent research topic, which is the tube-based model predictive control method for joint angle tracking with functional electrical stimulation and electrical motor assist. Every year, almost 17,000 new people with spinal cord injury occur in the USA. People suffering from neurological disorders such as SCI lost control to the limb muscles. Functional electrical stimulation have been used to restore muscle functions such as hand grasping, cycling, and walking. One of the biggest challenges of FES rehabilitation is rapid onset muscle fatigue. Conventional feedback controllers usually have non-optimal solution that easily to cause overstimulation and more fatigue. A promising solution to this is to use a hybrid device that combines FES and electrical motor assist. The integrated system may delay the onset of fatigue by reducing the overall stimulation duty cycle. However, the integrated system is actually redundant due to the simultaneous use of FES and motor. Thus, how to optimally allocate motor and FES input will become a challenge. Model predictive control is such an optimal control algorithm that can deal with the aforementioned challenges. Previous work has been done to optimally allocate control efforts from FES and motor. However, those are only for linearized system, and robustness was not well described in those controllers. To address the challenges of FES control and distinguish from previous MPC controllers, I designed a terminal controller that used the Lyapunov-based control strategy for stability and feasibility analysis, applied a fast optimization method to achieve tracking objective, and can be robust to modeling uncertainties and environmental disturbance. This is a single degree of freedom lag extension model, and the model is controlled by motor and FES. The control objective is to let the extension angle tracking desired trajectory. This is a structure of a tube-based MPC, which consists of nominal MPC without disturbance and feedback part, which deal with the modeling uncertainty and disturbance. The objective is to get optimal FES and motor input that minimizes the cost function. To ensure the stability, we added terminal cost function, which made the final state of each prediction horizon. The terminal cost value will asymptotically go to 0. To achieve this, the terminal controller was designed. The total cost function is monotonically decreasing by choosing the gain condition and weight matrices cost function properly. And we designed the feedback controller only for motor to compensate for modeling uncertainty and disturbance. By the outcome of analysis, the error between the nominal state and real state will ultimately enter in invariant set, thus the overall UUP stability will be assured. This shows the results of simulation. Two controllers, a nominal MPC without feedback and MPC with a Q-based feedback controller. The root mean square error of the nominal MPC is 50% greater than the Q-based MPC. This significantly shows the improvement of the Q-based MPC. This figure shows the FES motor input allocation and also the ability despite different input saturation levels.
The topic of my report is modeling-free inversion-based iterative feed-forward control for piezoelectric actuators. I will introduce in 3 aspects. PEA has the advantage of large output force, low power consumption, high control accuracy, and so on. This is the PEA. The PEA is widely used in precise positioning, optics, and other fields. The mathematical expression is modeling-free iterative learning control. It just has one parameter alpha. U0 is initial control, K is iterative circle, YK minus 1 is iterative output, UK minus 1 is iterative input, and YD is reference input. The Y and U contain a lot of information about the controller system. This is the control structure, where OK is control output, YNK is disturbance or noise. This is the experiment platform. The PA, the degree of freedom of motion is one-dimensional. Standard stroke is 0 to 80. Rated voltage is 0 to 120, and rated frequency is 0 to 50. Reference input has 3 types: single frequency signal, compressed input signal, and triangle wave test signal. The paper defines relative to normal as the equation to compare peer control and iterative learning control. Those pictures are experimental results, modeling-free iterative learning control. The T is sampling frequency. Those pictures are experimental results of peer control. The table is relative to normal of peer controller and MRFC. From the table, the iterative controller is far superior to peer control. The accuracy of MRFC is 10 times better than peer control, such as 30. That's all story of my report. Thanks.
My name is Fahad Al-Jahani, and I am a PhD student at CAST. This work I did with Professor Mariam Lalig. We developed an iterative algorithm for appropriate basis function selections. Modulating functions method is an asymptotic estimation method which provides accurate and robust estimations for different classes of systems. In the case of time-varying unknown, as in equation 1, the method required the decomposition of the unknown into predefined basis functions. The estimation performance will depend on the nature of the predefined basis functions, which in some cases are not easy to determine. Therefore, there is a lack of analysis of selecting appropriate basis functions. In our work, we are proposing an iterative algorithm that determines the basis functions framework. Then we will validate the proposed algorithm in distributed solar collector for real solar irradiance profiles. The solar collector model is represented in PDE form as in equation 2, where capital T is the temperature, U of T is the fluid velocity, and S of T is the source term. Our objective is to estimate the source term S of T from output measurements T out. Here is the definition of modulating functions. There are 2 properties must be satisfied to call phi of t modulating function. The first property is that phi of t must belong to space C of order L, And the second property is that phi of t and its derivative must be 0 at the boundary. One advantage of using modulating functions method is that it transfers the estimation problem to algebraic linear system. By following the 5 steps, we can transfer the PDE model into algebraic linear system. Then we can estimate the unknown capital gamma by taking the inverse of A. Next, I will talk about combining dictionary learning algorithm and modulating functions method. Figure 3 shows the training procedure of our proposed algorithm. The dictionary learning step allows the determination of appropriate set of functions to decompose the unknown, while modulating function step allows the non-asymptotic and robust estimation of the projections coefficients. Here are the results of the training procedure. We considered 50 profiles of real solar irradiance, and we selected the number of bases to be 28. Figure 4 shows the result of the updated dictionary, and Figure 5 shows 6 profiles of the source terms. We next validate the resulted dictionary by providing a new source term that has not been considered in the training process. Figure 6 shows the exact and estimated source term, and Figure 7 shows the error between the exact and estimated source terms. In the end, we develop an iterative method for estimate real solar irradiance profile, and the proposed method provides a numerical basis that accounted for modulating functions method. For the future work, we will study the proof of convergence, and we will extend the proposed algorithm to line estimation.
Hello everyone, my name is Zhu Chen and I'm from University of Buffalo. Today we are happy to present our work, Deep Iterative Learning Control for Controllers Trajectory Tracking. There are more and more drone applications nowadays. However, it is still challenging for drones to have high precision tracking. Improved drones' trajectory tracking accuracy can expand drones' applications to cluttered or compact working environments. Motivated by the feedforward learning form in iterative learning control, this study proposes a deep iterative learning control method to improve system performance by learning from the system's previous tracking knowledge. We first train a neural network to map the reference trajectory to the drone's tracking output, then design a learning filter to take the predicted information as its input and output the feedforward learning signal to enhance the drone's tracking performance. Suppose we have a stable system P with baseline controller included. When P tracks reference R, the tracking error without learning is E1. In order to reduce the tracking error E1, we design a learning filter L to generate a learning signal H, which is added to the feedforward loop of the system. With the learning signal, the system P's actual tracking error E2 is made to be smaller than E1. We train a neural network to predict the tracking error EP when the system tracks the same reference R, and EP will be the input of the learning filter L. Therefore, the deep LC consists of two components, a STM model and a learning filter. Next, we will explain the two components one by one. We choose the long short-term memory network to enable the sequence-to-sequence prediction. The neural network consists of a sequence input layer, an LSTM layer, a fully connected layer, and an output layer. We design various rectangular shape reference for the drone to track, and we collect the tracking information as the training data. We assume that the prediction is accurate enough, and we design the learning filter by utilizing the system dynamics. We first relate the tracking error E1 to the tracking error E2 by a system TE, which lumps the system dynamics P and the to-be-designed learning filter L. Then we design a learning filter to make E2 smaller than E1 in the sensor-to norm, and the learning filter design problem is transformed into a convex optimization problem, which can be solved efficiently with the help of MATLAB software. We conducted the drone's tracking with and without adding the learning signal, and the results show that the tracking performance is enhanced by adding the learning signal. In this study, a neural network model is trained to predict the system's tracking performance. A learning filter is designed based on the system dynamics to generate feedforward learning signal for system performance enhancement. Experimental tests with a quadrilateral have been conducted to validate the effectiveness of the proposed method.
Hi, I'm Shirin Afzali from University of Georgia, presenting our work on optimal lighting control in greenhouses equipped with high-intensity discharge lamps using reinforcement learning submitted to ACC 2021. This is the work I did with Sahan Mosharafian, Professor Mark Laniersil, and Professor Jawad Mohammadpour. Using supplemental lighting in greenhouses has potential for improving plant growth. However, Lighting cost accounts for a large portion of greenhouse expenses. LEDs are a popular choice for greenhouse supplemental lighting, but HID lamps with discrete output light levels are still being used. In this paper, the supplemental lighting control problem in greenhouses equipped with HID lamps is formulated as a discrete constraint optimization problem, and the optimal solution is found through combining method of multipliers and Q-learning while considering plant daily light integral, or DLI, a Markov-based sunlight prediction, and variable electricity pricing. Therefore, the goal is to minimize lighting costs subject to supplying sufficient light to the plant. Green Towers lettuce is considered here, which needs a DLI of 17 mol per square meter per day. To predict sunlight, time-variant Markov model is considered. Method of multipliers is an approach for solving constraint optimization problems, which uses augmented Lagrangian. The novelty of our method is in using Q-learning, which is a reinforcement learning algorithm, to find the argmean of the augmented Lagrangian. The goal of the reinforcement learning agent is to maximize a discounted reward, which is received based on the action taken at different states. In our problem, states are time steps and actions are the possible HID light levels, and the reward function is defined based on the cost function. We compared the proposed method to a baseline, which is optimal but assumes prior knowledge of sunlight, which isn't realistic. Also to a heuristic method, which provides enough light to reach a constant PPFD. Different test days in April and December were examined, and our method reduces cost significantly. Also, we evaluated our method throughout a whole year, and it showed about 44% cost reduction compared to the heuristic method. In this paper, a new strategy was developed to find optimal HID lighting in greenhouses through combining Q-learning and method of multipliers. The proposed approach showed a significant cost reduction compared to the heuristic method. Thank you.
Hello, I'm Colin Zavislak, and I'm presenting on AUV buoyancy control with hard and soft actuators. So the problem we were examining in this paper is that for small body, highly maneuverable AUVs, it can be difficult to operate and maintain one's depth in confined spaces. So in looking for a potential solution, we asked ourselves, how do marine animals maneuver so efficiently? And the answer is that they use a combination of hard and soft actuators. Their fins serve as hard actuators, propelling them forward, while an organ called the swimming bladder allows them to adjust their buoyancy, serving as a soft actuator. We wanted to mimic this on the AUV to get effective maneuvering. So we use inline pumps as hard actuators and a buoyancy control device with reversible fuel cells as a soft actuator. The buoyancy control device was able to perform electrolysis with the fuel cells and create gas to adjust the system's buoyancy. Taking this system and making several assumptions and constraining it to 1 degree of freedom, we get the free body diagram here on the left, and then via Newtonian dynamics, this equation of motion. Combining the equation of motion with the pump dynamic equations, which are the first 2 states, and the BCD equation, which is the 5th state, we ended up with this overall state space model for the system. For the control algorithm, beginning with the hard actuators, we used a proportional controller with a deadband. The hard actuators then maneuvered the system from our starting depth to our desired depth quickly, while the soft actuators generated gas. The hard actuators would then maintain that desired depth until the soft actuators had generated enough gas to make the system neutrally buoyant at our desired depth. At that point, the hard actuators shut off and the soft actuators take over, abiding by a proportional derivative acceleration control law to maintain the depth of the system. The overall results of this model and control algorithm can be seen here in these plots, where in the far left, we can see that in a hard actuator only scenario, the system maneuvers quickly from a depth of 1 meter to a depth of 6 meters and then goes into oscillations, pretty much indefinitely, but it consumes a lot of energy doing this. In a soft actuator only scenario, the system is able to maneuver successfully from 1 to 6, consuming very little energy, but it takes a very long time and is a very gradual and slow process. When we combine hard and soft actuation, the system is able to maneuver quickly and effectively from 1 to 6 meters, go into oscillation while the BCD generates gas, And then once it's generated enough and we're almost neutrally buoyant, the hard actuators shut off and allow the soft actuators to maintain the depth and save power, which is why you can see here in the energy curve that it flattens out over time. We quantified these maneuvers using a performance index, which is what is displayed in this results table here. And we can see that for a combination of hard and soft actuators, we actually achieved the best results. So in conclusion, by mimicking marine animals, we found that AUVs are able to maneuver much more effectively. Thank you for your time.
Hi, my name is Mariusz Matusiak. I am a PhD student at the WeA02 University of Technology in Poland. In this video, I would like to show you the results of my recently conducted research on microcontroller implementation of fractional calculus-based algorithms and its useful integration with MATLAB utilizing the MEX Separate Complex API. It's been a part of a large project developing a variable fractional order control of an unmanned aerial vehicle arm with 2 BLDC motors. One of the concerns of fractional calculus is its infinite memory effect. To evaluate a fractional order derivative of a function f of t in point t, one must consider all the previous values of t starting from t0. The problem is especially challenging for slower microprocessors with limited available memory, realizing time-critical tasks. The article describes a developed MATLAB tool being an extension of the middle-level implementation of numerical methods for solving fractional order differential equations and designing fractional order control systems. A significant improvement of the tool is the possibility of computing fractional order differential integrals of variable orders. Another advantage of the proposed solution is reusability of the same code used in both MATLAB simulations and on the target platform. Let's take a look at the comparison of computation times for 3 tested algorithms. The first chart presents calculating L binomial coefficients of the Grunwald-Letnikov fractional order backward difference using plain MATLAB script and the prepared function. The proposed implementation ran over 88% faster. In the second chart, we can see an implementation of fractional order derivative of a unit step signal with order switching from Ni1 0.2 to Ni2 0.7. Here the improvement reached over 91%. Finally, the step response of a system evaluated with the closed form solution has been measured, comparing MEX implementation and the LSIM solver from the FOTF toolbox. Computation time was reduced this time by 71%. A special virtual environment on the CodeOcean platform with the shared code has been prepared. The code is publicly available, so I encourage you to visit this website at the link below. Right after you visit the CodeOcean website, you will see a README file explaining how to build each of the CMEX files separately on your machine. You can download the code and run the build all and run shell script to build all of the files, or perform the reproducible run remotely without having MATLAB installed. The library is still under development, so more features will become available in the future. Thank you for your time. Should you have any more questions, please contact me directly at my email address.
Hi, my name is Alan Basso and I will be presenting our paper, Global Asymptotic Tracking for Marine Surface Vehicles Using Hybrid Feedback in the Presence of Parametric Uncertainties for the 2021 American Control Conference. In this paper, we propose a hybrid adaptive feedback controller for global asymptotic tracking control for marine surface vehicles in the presence of parametric uncertainties. The hybrid feedback is derived from a family of potential functions and employs a hysteretic switching mechanism that is independent of the vehicle velocities. Moreover, the tracking references are constructed from a given parameterized loop and a speed assignment specifying the motion along the loop. So we assume the following structure for the equations of motion, where G is the configuration containing the position orientation, nu is the velocity, m is the generalized mass matrix, the term in the brackets is the geometric acceleration, d of nu is the vector of drag forces, tau is the control inputs, and where we have assumed that the effect of ocean currents and other unmodeled dynamics are captured by a constant bias b. Given a parameterized loop gamma of s, where s is a path parameter, which can be interpreted as a time scaling, we propose the following hybrid reference system. Here, ud is the desired speed, which is the output of a second-order low-pass filter with input mu In this way, continuity of the velocity and acceleration references can be ensured. Moreover, kappa is the desired tangent vector expressed in the desired frame, and the desired acceleration is given by this expression. Using these error coordinates, we obtain the following hybrid error system. The problem can be stated as follows. We remark that this speed assignment ensures that the magnitude of the linear desired velocity is equal to ud. We now define the following potential functions whose gradients will determine the proportional control action. Here q is a logic variable, rho 1, 2, 3 is simply the heading angle represented in different intervals, and where log r is the principal logarithm of r, which entails that rho 3 is in the interval minus pi to pi. The hysteretic switching mechanism is defined through the flow and jump sets C and D and the jump map G1. The flow sets are visualized in figure 1, where C1 is the blue curve, C2 is the red curve, and C3 is the green curve. The following lemma then constrains the offset O and gains K3 and K such that the change in the potential functions over jumps are non-positive. Then, by defining the modified velocity error nu s and the modified velocity reference nu m through this differential equation, where lambda is a gain matrix, and y theta is a strictly passive function, and now assuming that the unknown model parameters are lower and upper bounded and that the drag forces are linear in the parameters, we propose the following adaptive hybrid control law. Here, capital phi is a regressor matrix, var phi is a strictly passive function representing a derivative action, and dv sub q is the proportional action. The main theorem shows that the problem statement is solved. Finally, we show some simulation results for a scale model shape with a desired speed of 0.1 meters per second and an ocean current of 0.05 meters per second. Thank you for your time.
Hi everyone. The work I present today concerns the control of infinite dimensional systems. This type of system, such as the continuous crystallizer, which will be my driving example in my poster, are complicated to control. Indeed, high-order representations of systems or infinite dimensional representations usually results in high-order or infinite dimensional controllers, which are not suitable for implementation. From there, the other possibility would be to use a reduced order model of the system to be controlled in order to obtain a lower order controller. But this lower order controller, if suitable for implementation, will not be tailored to the actual systems. These two strategies can be referred to as model-based control, and they both underline the importance of model order reduction when it comes to infinite dimensional systems, whether it is to reduce the controller or to reduce the model of the systems that is used for design. In some past work, I showed that model order reduction can also be used in a data-driven control context in order to obtain a low-order controller that is tailored to some data of the system. So the objective of the work I'm presenting today is to highlight the relevance of this approach to control infinite dimensional systems, and it is based on the Lerner framework. In addition, I will compare in my poster this technique with a data-driven structured H-infinite synthesis that has been developed specifically for infinite dimensional systems. Regarding my application, it consists in a continuous crystallizer, which is a common process in the chemical industry. It is described by an infinite dimensional transfer function here that exhibits sustained oscillations. The problem is that this oscillation may degrade the quality of the crystals that are produced. So the control objective is to stabilize the plant around a desired steady state. And for that, as I mentioned earlier, in my poster, I use the linear data-driven control approach, which is the approach I developed earlier, in order to control this system. So from samples of the frequency response of the system, I can construct first achievable specifications, which is very important in data-driven control, before moving to the core of the technique, which is the obtention of a reduced controller through the Lerner framework. And then I can move to closed-loop stability analysis, still in a data-driven framework. All these steps are detailed in the poster if you have any question. In the end, the poster shows that Lerner data-driven control is computationally efficient, does not need a stabilizing controller, and that the leverage that the user can use are controller order and specifications. To that extent, future work will focus on a better choice of the specifications, but also on understanding better the impact of order reduction on closed-loop performances. Thanks for your attention, and if you have any question, feel free.
Hi, my name is Carlos Armenta, and I'm a PhD candidate at the Polytechnic University of France. In this work, we present an improvement of a classical Ponty-Green minimal principle-based algorithm used to solve hybrid powertrain optimal energy management by relaxing the tolerance on some intermediate steps. You're reducing the computational cost by reducing the number of evaluation of a function called the Hamiltonian, which has the highest computational cost in practice. This algorithm aims to minimize the fuel consumption of a powertrain and to reach a final state of charge for the battery pack. This under the constraint that the control input is bounded in an interval. The boundary and minimal principle establishes the condition for optimality by defining a function called the Hamiltonian, which relates the fuel consumption with the battery dynamics by means of a parameter called the cost state. This condition for optimality consists in the minimization of the Hamiltonian by means of the control input, and also indicates the way the cost state has to vary or to change over time. We consider the assumption that we have a perfect battery pack and also a perfect DC-DC converter. This has for consequence that the cost state is a constant parameter to be determined. The classical algorithm does the Hamiltonian minimization by defining a grid, a control grid, where the Hamiltonian has to be evaluated. This control grid has an accuracy defined as the difference between the maximum and the minimum of the control input, maximum admissible control input, divided by the number of nodes. And the cost state is determined by a bisection algorithm, which finds the roots of a function which relates the final state of charge and the cost state. This is an inefficient algorithm because we don't need to evaluate at each node of the grid set. And also, if the grid doesn't have the accuracy enough, the algorithm may not converge. To solve this problem, we propose an improvement that consists in beginning with a coarse grid and to refine it only when it's necessary and only in the interval where we know the optimal solution is. This reduces the computational cost and also ensures the convergence of the algorithm. We can see the illustration in the example. When we see the relationship between the number of evaluation for the classical and the improved algorithm, we can see a high improvement, not only in the Hamiltonian evaluation, but in the required time to solve this problem. Thank you very much, and I look forward to answer all your questions.
This paper develops a seasonality estimation scheme for advertising campaign, which is very critical for optimal budget delivery and performance management. Advertisers partner with the demand-side platform, DSP, to compete with other advertisers for impressions to show their ads to a targeted audience. Advertisers specify a total advertising budget for each campaign they set up. The DSP is tasked to spend the budget in the optimal way to maximize the return on investment performance. Feedback control has played an increasingly important role in solving the optimization problems. The development of control designs faces many challenges. One such challenge is that the internet user traffic is periodic. The available impressions to a specific campaign show a time of day seasonality periodical pattern. Due to the difference in targeted audience and the ever-changing competing landscape, the pattern varies from campaign to campaign. This seasonality, if not compensated appropriately in the feedback control design, would result in suboptimal campaign performance. For example, advertisers may end up paying an unnecessarily high cost for impressions during a time when the competition is intense for limited available impressions. In this paper, we proposed a two-step seasonality identification scheme, including a normalized gradient design for the estimation of time-varying plant gain, and a normalized least square design for the identification of the seasonality model. The identification scheme is now running alongside the feedback controller in Verizon Media DSP. Effectiveness and robustness of the proposed scheme are demonstrated with both simulation and experiment results from real advertising campaigns with the DSP at Verizon Media.
Hello, my name is Emil Lavchev, and I'll be presenting a paper called Thermal Comfort Optimization for Groups. This work was performed in collaboration with Diego Ramirez and Daniel Nikovsky at Mitsubishi Electric Research Labs. In this paper, we address the problem of thermal comfort optimization in the group setting. Specifically, we're interested in places like the modern open office, where it's difficult for individuals to become comfortable for various reasons. This leads to reduced productivity, increased employee costs, and generally unhappy office workers. But research suggests that if we can make people comfortable in the open office, we can decrease their error rates, make them more productive, and even increase the happiness of these offices. So in this paper, what we would like to do is use the existing behavioral paradigm of people to learn their thermal comfort preferences. Then we want to use the existing HVAC infrastructure with minimal additions so that we can deploy this in as many offices as possible. The goal is to learn how to control the existing HVAC units to optimize the comfort of the users. So in this paper, we focus very specifically on replacing the intuitive models that each user has in their head. Specifically, the model about how comfortable I feel based on the temperature now, and the model about the temperature in my location in relation to the temperature at the thermostat, which ultimately controls the behavior of the HVAC system. We implement a data collection experiment in a real open office in Japan. This was performed in the summer of 2019. There are 5 HVAC systems in this office, 39 desk sensors that were added, and 18 users. Data was collected for 10 days and sampled at 1-minute intervals, giving us 12,000 data points on which to learn. Our users were able to interact with the system at any time, and they were free to choose which HVAC system to interact with. We use predictive neural network models to learn a description of the room thermodynamics. In other words, to learn how the temperature and humidity at the location of the users relates to the temperature and humidity at the location of the thermostat. We then use online optimization to choose the best HVAC parameters to optimize user thermal comfort. We use online optimization because in this paper, we would like to allow the users to change their seating locations throughout the day. Experimenting over many possible seating arrangements and with 2 different kinds of individual thermal comfort models, both one per user and combined for similar users, we find that the approach proposed in our paper outperforms the baseline methods by a factor of at least 2-fold. I look forward to speaking with you at the poster. Thank you.
The title of our presentation is Ultrasound Bubble Control for Blood Clot Deformation in a Vessel Connected to a Pulmonary Artery. Investigators from the University of Michigan have developed a non-invasive technique that can break up the clots in deep veins. This figure shows that blood flow in a pig blood vessel is blocked by a clot. As you can see in the right figure, after a 5-minute histotripsy treatment, blood flow restored. But the open problem is that so far this issue has not been studied scientifically. The bubble dynamics, which described by the Rayleigh-Placid equation. As you can see, the up figure indicates the curve of the bubble radius, and the down is the collapse pressure as a function of time.
As I've mentioned before, this study is related to the vessels which are connected to the pulmonary veins, and the clot dimensions is considered due to the vessel dimensions. Using these parameters, the blood and clot are simultaneously simulated respectively as a flow and a solid. The inflow pressure of the vein inlet is specified to calculate the amount of pressure on the clot at various times. In order to have an exact numerical simulation which covers the relevant features, good quality mesh generation is necessary. In this study, the tetrahedral elements are used for the entire field meshing. As it is mentioned before, the goal is to control and to apply the pressure field generated by the collapsing bubble using ultrasound to fracture bubble clots. To find the minimum pressure for clot fracture, a coupled simulation of blood and clot has been done numerically according to the different initial pressures generated by the bubble collapse. Thus, in this section, different values for the pressure applied on the clot surface from the different bubble collapses are used for simulating the behavior of the clot, and equivalent stress and total deformation of the clot surface are calculated for each input pressure. Each amount of pressure causes a specific rate of stress, and as you can see in this diagram, the minimum required pressure to pass the yield stress is about 0.2 megapascal. For more clarification, we did some different simulations with different clot dimensions to have a better conclusion over comparison of the results. In this slide, you can see the velocity contour and streamlines of blood flow over the clot and also the total deformation of the clot in one of these simulations. After simulating bubble dynamics, calculating mean required pressure for clot deformation, we can select proper ultrasound frequency to reach the desired pressure to cause a bubble fracture.
Hello, I am Max Edmond from the University of Arkansas, and I worked with Paolo Mercarelli from Leuphana University of Lüneburg on our paper, Fast Finite Time Sliding Mode Control with Optimal Reference Trajectory generated by Model Predictive Control and Robust Robotino Motion Planning with Saturating Inputs. Displayed here is a Robotino. It is an omnidirectional robot that we use to develop our control strategy. It and other robots like it have multiple uses in factories and various other workplaces. This is the control scheme block diagram. It is shown in our paper in order to give the reader a better understanding of the control strategy. We start with 3 reference signals, which together with the decoupled MPC, decoupling controller, and mechanical model, output 3 desired optimal reference trajectories for the sliding mode control. The sliding mode control is used in order to account for external disturbances and errors, and also the internal error provided from the inverted electrical drives and filter. Additionally, we have an anti-saturation strategy, seen B-tan-H, which accounts for the saturation present in physical systems. When considering the given system, which is the decoupled X motion, the following sliding mode control law, which is broken down into 2 parts, 1 part equivalent and 1 part corrective, globally stabilizes the system in the presence of stable uncertainties, bounded disturbances, and in the absence of saturated inputs. However, this breaks down in the presence of saturated inputs. Therefore, we are able to use the theorem, which is proven in the text, in order to avoid saturation and to maintain the robust global asymptotic stability. The results of this strategy can be seen by observing the tracking shown in the diagram below. The pathing of the diagram is a bit unconventional in order to show the robustness and effectiveness of the control strategy. Additionally, this diagram shows an example without saturation or error. However, using saturated inputs or introducing error results in much the same diagram with no visible difference. To summarize, we used model predictive control to generate an optimal trajectory, sliding mode control to account for errors and disturbances, and an anti-saturation function in order to deal with the saturation present in physical systems. We would like to thank the USAC program with special thanks to Dr. Stephanie Seewald, USAC Resident Director at Leuphana University of Lüneburg, for giving us motivation, encouragement, and for the perfect organization of the USAC Exchange Program during the spring and summer of 2020. Lastly, if you have any questions, please feel free to stop by and ask them during the rest of the session. Thank you very much and have a wonderful day.